Now continuing our discussion on likelihood functions and the maximum likelihood estimate, let's look at the likelihood inference for several parameters. So we can extend our concept easily to several parameters. Let's call them lambda k, which we combine to form a vector. So we have k parameters. In the likelihood function, for this vector, so once again the product over n PDFs and the log likelihood is the sum over n terms, each of which is the log of a PDF. To find the maximum of the likelihood function, we set the partial derivatives to 0. And the values, say lambda k hat, which satisfy the system of equations obtained this way, are the maximum likelihood estimates of the parameters. So basically, we get a system of equations that are basically obtained by setting the partial derivatives with respect to each of these parameters. Equal to 0. Now the error interval also becomes an error volume, and its surface will be defined by the drop of the log likelihood by half. So now we have to assume that this defines a closed surface in the parameter space, and in 2 dimensions that is just a closed contour. So as an example, let's look at the likelihood analysis for a signal with background. So we want to fit a normal distribution with a linear background to a given sample. So the PDF in this case so this piece is the linear background. And this is the normal distribution. So the normal distribution has unknown mean, mu, and standard deviation, sigma. Other parameters are not independent because f has to be normalized in the given interval. So we can eliminate one parameter. Assuming that the normal distribution is negligible outside the interval, the norm D is given as half of theta 1 x max square minus x min square plus theta 2 times x max minus x min plus theta 3. So, which allows us to write the normalized PDF. We have defined new parameters, theta 1 prime and theta 2 prime. Simply the ratio of theta 1 and theta 3 and that of theta 2 and theta 3. So likelihood function is obtained in the usual way by inserting the observations of the sample into the log likelihood. This expression is maximized by again solving the system of equations generated by setting the partial derivatives to 0, and that gives us four parameters, and from those we can get the fraction of signal events, which is basically given by theta 3 by d, and this is, can be verified, comes out to be Now, frequently we encounter a situation that we have to compare measurements with normally distributed errors to a parameter dependent prediction. For example, when we fit a curve to measurements. So let us assume that we have n observations we denote as xi, each following a normal distribution with variance delta I square. So we can basically write so these observations are basically to be compared with a function di of theta, and the log likelihood This can be written as minus half times the sum over xi minus ti of theta square by delta I square plus a constant term, which is log of 2 pi, plus the log of delta I square. The first term of the sum corresponds to a chi-square distribution. So you can identify chi-square sum over xi minus ti theta whole square by delta I square, the sum over I. Now for parameter inference, we can omit the constant terms in the log likelihood expression, which is the last two terms. So omitting the constant terms, basically gives us the log likelihood equals minus half of the chi-square. So this basically tells us that minimizing the chi-square is equivalent to maximizing the log likelihood. The maximum likelihood estimate of theta is obtained from a so-called least square or chi-square fit. Since you obtain the error in the estimates theta hat from the change in the likelihood function by half, this means that chi-square increases in the range by 1 unit. Next, let's discuss the likelihood of histograms. For large samples, it is more efficient to analyze the data in form of histograms than to compute the likelihood for many single observations. The individual observations are classified and collected into bins, where all events of a bin have approximately the same likelihood. We can then compare the number of entries of a bin with the parameter dependent prediction. A number of entries is denoted by di in a bin I, the ith bin, follows a multinomial distribution. Where for each bin, the probability is computed as a function of the parameters. In fact, it's more appropriate to denote it by theta, vector theta, because we're taking into account more than one parameters. So for a total of n observations, the expectation of the number of observations in bin I is denoted as n times pi theta. And this is what we have seen for multinomial distribution previously. Usually, the number of entries of an individual bin is small compared to the total number. So in such cases, we can apply the Poisson distribution. So let's say the likelihood for Ti expected and Di observed entries according to the Poisson distribution is given as Li theta e to the power minus Ti times Ti to the power Di by Di factorial, where Ti is the expected entries and Di's are the observed entries. The log likelihood is simply given as minus Ti plus Di times log of Ti minus the log of Di factorial. Now, since factors independent of theta are irrelevant for the likelihood inference, we can omit the term with the factorial. So the log likelihood of the complete histogram with total number of bins as capital B is given by log of L theta is a sum from I equals 1 to B, sum over I, so minus Ti plus Di log Ti. So the parameter dependence is hidden in the quantities Ti. The maximum of this function has to be determined using numerical methods. Now, if you look at histograms with background, so that is the case if the measurement is contaminated by background, which follows the Poisson statistics with a mean B, then the expression for the log likelihood gets modified as follows. Where Bi is the mean obtained from the Poisson statistics that is followed by the background. Of course, a simple subtraction of the average background would have underestimated the uncertainties. And a further modification of this expression is necessary if the expectation value of the background itself is subject to uncertainties. Now, speaking of the Poisson distribution, if you look at its asymptotic limit with increasing mean value, the Poisson distribution approaches a normal distribution with variance t. So therefore, for high statistic histograms, the number of events in a bin with prediction t theta is described by a distribution of the form this function, for which the log likelihood is again given as for large t, the logarithmic term is an extremely slowly varying function of t. So therefore we can neglect it as well as the constant term, and then we find that for the whole histogram, log L is basically minus half times a sum from I equals 1 to I equals b di minus di square by di, and this is nothing but minus half times chi square. So if the approximation of the Poisson distribution by a normal distribution is justified, the likelihood estimation of the parameters may be replaced by a chi-square fit, and the standard errors are given by an increase of chi-square by 1 unit. Next, let us look at something called the extended likelihood. So when we record n independent multidimensional observations, of a distribution that depends on a set of parameters which we denote by the vector theta. It may happen that these parameters may also determine the rate. The expected rate. Lambda theta is a function of theta. In this situation, n itself becomes a random variable like xi. So we have to multiply So we basically have to multiply two probabilities. The probability to find n observations which follow Poisson statistics, and the probability to observe a certain distribution of the variates. So the likelihood basically becomes a product of this Poisson distribution times the usual product over the PDFs corresponding to the observation of the x's. From here we can always compute the log likelihood. And once again we can omit the last term in the likelihood analysis because it does not depend on theta. But this is where we'll deviate from the discussion on maximum likelihood estimation for the time being, and we'll discuss a slightly different topic, which is the inclusion of constraints in parameter inference. So basically the interesting parameters, the parameters that we are investigating, are not always independent of each other. They're often connected by constraint equations like physical or geometrical laws. So let's say we assume that we have n direct observations xi which are predicted by functions ti of a parameter with p components as well as k constraints of the form and if we also assume that the uncertainties of the observations are normally distributed and the constraints are fulfilled with a precision delta k, and basically write the expectation of ti theta minus xi square so delta I square denotes the uncertainties in the observations. And similarly we have for the constraints Then the chi-square can be written as, it's a sum over two pieces. So we minimize chi-square by varying the parameters and obtain their best estimates at the minimum of chi-square. A corresponding likelihood fit would maximize Now, in most cases, the constraints are obeyed exactly. That would imply that delta k is 0. That would mean the second term diverges. And usually this difficulty is avoided through three different procedures. The first would be use the constraints and reduce the number of parameters. The second method are the constraints are approximated. By narrow Gaussians. And lastly, the use of Lagrange multipliers and some adjustments are applied to them to satisfy the constraints. So this is where we'll end our discussion. We will not go much into details on how these constraints are handled. So this wraps up our discussion on maximum likelihood estimation and its extensions. Next time we'll look into the scenario where certain parameters are undesirable or what are known as nuisance parameters, and we'll try to look into some detail how we handle them.